Hello everyone, my name is Luca Visinelli. I will be a fellow at the Tsung-Dao Lee Institute starting this coming fall. This is my presentation for the Summer Camp 2021 for the School of Physics and Astronomy. I will discuss future probes for physics beyond the Standard Model. Before getting into science, I will briefly introduce myself. As I said, I will be a fellow at TDLI in the Astronomy Division and an associate professor at the School of Physics and Astronomy at Shanghai Jiaotong University. I am currently a Marie Curie Fellow at the Italian National Institute for Nuclear Physics, or INFN, before coming to Shanghai. I have graduated from the University of Utah with Paolo Gondolo, working on particle physics and cosmology. I have then been a postdoc at Nordita in Sweden with Catherine Fries and at Grappa, Amsterdam with Christoph Weniger. My research directions explore the possibility that new physics exists beyond the standard model of particle physics, using data from astrophysics and cosmology. I want to know what are the dark matter and the dark energy, two mysterious components of the universe for which we see the effects through gravity, but we do not yet have a microscopic mechanism in terms of a new particle or a modification of gravity. Dark matter and dark energy cannot be simply explained within the standard model, and new physics is required to understand them. Let's first consider dark matter, which has no charge, is long-lived, and interacts feebly with the ordinary matter in the universe. We know that dark matter interacts through gravity. However, we do not know how strong the other interactions are. I refer to the weakly, electromagnetic, or even a new fifth force interaction. For this, different models predicting different interactions other than gravity can be put at test in the laboratory or using astrophysics and cosmology searches. These searches are usually divided into three main categories, namely direct detection or laboratory searches, indirect detection searches, and collider phenomenology. The direct detection techniques use the dark matter in the solar system halo, which is expected to scatter or interact with a laboratory device. The indirect detection looks for byproducts of dark matter annihilation in the galaxy. Colliders can be used to produce dark matter particles in the accelerator. So far, my research has mainly focused on the first two strategies of direct and indirect detection in relation to light bosons. Bosons are an attractive candidate for beyond the standard model theories. They are expected to be produced copiously in the early universe as a manifestation of string theory and naturally emerge in relation to the spontaneous breaking of asymmetry. It is possible to construct theories which include new bosons of masses spanning from the Hubble rate today, the Hubble constant h0 equal to 10 to the minus 33 electron volt, up to the inflation scale at around 10 to the 13 GeV. The same modeling can then be applied for dark matter, dark energy, and inflation. One particular boson I have worked with is the axion, introduced in the 70s by TDLI director Professor Wilczek and now actively looked for in many experiments around the world. If the axion exists, it's possible to search for it through the modification of electromagnetism that comes along with its presence, as first shown in 1983 by Pierre Sikivi, University of Florida. I have contributed to writing down the design for a direct detection axion search with mass in the microelectron volt at the Frascati National Laboratories in Italy. On the theory side, I am mostly interested in the indirect detection of axion dark matter, once they interact with the magnetic field surrounding a neutron star. Observing a target neutron star in the radio could reveal that this object is eating up axion dark matter, converting it into a radio signal. So far, there have not been dedicated searches, and I am about to start a collaboration for tackling this aspect, which could beat the sensibility in laboratory search and could corroborate direct detection if successful. At TDLI, I will carry on these research lines that mix astrophysical considerations with particle physics and cosmology, with an eye to the experimental side and to the possible reveal of a signal. I have extensively worked on axions and other light bosons. With several impactful papers, I push for being among the protagonists of discovering this particle in the future. My other interests include dark energy, on which I have written papers that explain how to look for its existence in cosmology through the cosmic microwave background data and indirect detection experiments. I will carry on this line of search in the following years when new data emerge. To sum up, I give you the motivation why a career at TDLI should be considered. The Tsung-Dao Lee Institute is a modern and fast-developing center that covers all aspects of physics, from the astro division to particles to quantum, and we work in close contact with the experimentalists at Shanghai Jiao Tong University. The core scientific division is composed of renowned world leaders in their respective fields, which pursue cutting-edge science, working on interdisciplinary and international collaboration. Please feel free to reach me through my email in case of further question, and visit my website to discover more of what I study. Thank you a lot for the attention.